The next operator that we are going to describe will be the filter operator, and this is the operator that is called upon one data stream, for example, of generic type T, and the resulting will be another data stream object, but the generic type will be exactly the same. What is the purpose of this operator? The purpose of this operator is to filter or to remove some of the values and keep the other values into the data stream. Um, how is this operator defined? Uh, we define it with calling filter on the source data stream, and that filter expects an object of the functional interface filter function. The filter function is a functional interface, generic functional interface with only one generic type, and that's the type of the source and the destination data stream. In this case, we have a data stream of integers, and over there, we want to filter to keep all of the values in the data stream that are different than 0. So what do? We just implement this Boolean filter function where we have to set up a condition onto that which values are going to be left in the stream. And we can use this filter operator really easily into what we have previously had in our application that we have developed it so far. For example, over here we are actually ignoring all of the sensor data that are not produced from the sensor ID 4, 8, 10, and 13. So we can actually write a filter method over here that will filter all of those first and then call the flat map over here. So we can say new filter function over here, and we say this one will return true. That means it will keep the sensor data into the stream only if sensor data dot get sensor ID. Let's maybe keep it into a variable so we don't call the get method all the time. Sensor ID equals to sensor data dot get sensor ID. So return. This is actually long. Yep. So keep the data in the data stream only if the sensor ID is 4L or sensor ID is 8L or sensor ID is 10L or the sensor ID is 13L. L stands for long over here. We can definitely do this with lambda expression. It can be this way, and this can also be with one lambda expression as we previously defined. So nothing is going to change in the output over here that we had previously defined. If I run the application one more time, actually we have a mistake. The return type of function. So yeah, it's probably over here because we're calling the operators in chain over here. We could do it this way, filtered data stream, and then the filtered data stream will be flat mapped, and this result should be saved into a data stream of sensor data named sensor data flat mapped, just like we use it in the next print operator. Okay, let's give it a try now. Everything should work now, I think. Nope, not again. Sensor data stream dot filter. Probably we shouldn't have changed this into lambda expression. This is complicating the things a bit for the type inference here in Java. Okay, let's give it a try with anonymous classes if this is going to work. Yeah, this works perfectly. So that was the issue because the return type of the method got lost in this situation due to the lambda expressions, but now it looks okay. So as we can see, we have the same thing, 1, 2, 3, 4, the same values over here. Yep, same value, same timestamp, just like we wanted it to be. Okay, then we can proceed with the next operator, and this is the one of the most important operators in Apache Flink, the keyby operator. So the keyby operator is the operator that is allowing us to make Apache Flink a distributed application, or to be more precise, this operator is allowing us to process the data into different task slots, just like we defined by the architecture of Apache Flink. So the keyby operator is being called on a data stream of type T, let's say, and the result is a keyed stream of type T again. This is doing the logical and both physical partitioning of a stream into disjoint partitions. So all records with the same key are assigned to a same partition, and they can later be processed on a different node in a cluster of Apache Flink. They can be processed in a different task slot, in a different task manager, etc. So we can provide the keying mechanism over here, and we could do it with maybe some getter method over here. So for example, in our scenario, let me just stop the application. In our use case, there are several ways that I can think of how we can process the data, partition the data. One is by sensor type. So we could do it by sensor type, maybe. That way we will have 4 partitions. One partition for the temperature sensors, one for the pressure, one for the carbon monoxide, and one for the humidity. So in that way, in one place, we can process all the data and do some aggregation, some calculations, some mathematical, statistical analysis over there on that data, and then print the results that we want. So I'm going to comment this so far. It was nice to learn the flat map and the filter, but I'm going to get back with the sensor data stream. So this sensor data stream over here was just the data stream of the objects that we were simulating. We can start it again so we can remind ourselves. Okay, here is it. So in our case, let's see how can we call that keyby operator. One way, as we said, is so the sensor data stream dot keyby. The keyby method expects a key selector. You can define the key selector with an anonymous class, something like this. Let's say that the key is going to be a string. So for example, if I want it to be the sensor type, just return over here sensor data dot get sensor type. And this is one way to do it. This can definitely be a lambda expression. This can even be method reference in Java, something like this. We don't even miss over here, if I'm not mistaken. Yep. So in this way, I will partition the sensor data stream into 4 partitions, and each of those partitions can be run distributedly on a given cluster. Another way that we could do over here is partition by the sensor ID, get sensor ID. That's another way that we could do it. And also another way that comes to mind is, for example, if I have the sensor data and concatenate the sensor type and the sensor data dot get sensor type and sensor data got get sensor ID. But this doesn't make any sense. Why? Because each of the sensor IDs are completely different. Okay, so if I just partition by the sensor ID, I will create how many partitions? Let's count. So I will create 13 partitions. And if I do it this way, I will also create 13 partitions. It will be, again, the same. So this is equivalent like partitioning the data into just by the sensor ID. In situations like this, when you want to make your application run in distributed fashion, it is most important to think of the number of the partitions that are going to be created. Okay, so in my application, I know that if I partition by the sensor type, I will have all the time exactly 4 partitions. So that means that I will create a cluster which will allow a parallelism of 4. So my cluster would either have 4 task managers, or the one task manager that I'm going to have will have 4 task slots at least. So this is how I can achieve a distributed execution of the whole application. So that's pretty much for the key by operator. I don't think that we can even print this operator, to be honest. Let's see what are we going to get if we print it. Probably I think that the same thing will be printed, but we won't know on which partition did, yeah, it's just the same thing, just the same data over here. So we don't know exactly on which partition this ended up. Later we can show how can that be demonstrated. Okay, let's just create a variable over here. So kit stream, let's just have it as a variable because we are going to use it in some of the other exercises. The kit stream is an object in the Apache Flink framework that is a generic, it's a generic class with 2 generic parameters. One, the type of the data that is being keyed, and second, the key of the partitions. If I go by get sensor ID, this would not work. I would have to put long over here because the sensor ID is long. Okay, let's get it back to get sensor type. Okay, the next operator that we are going to do is the reduce operator. The reduce operator can be called only on a kit stream, so it cannot be called on a data stream. It must be called on a kit stream. And what does this reduce operator does? So for each of the 4 partitions, this reduce operator will be called on each of those 4 partitions in our use case scenario, and it will produce a rolling reduce, or whenever a new element comes, it will combine it with the last reduce value and then emit the new value to the data stream that's the resulting type. So for example, if I have, what would be this? So for example, if I want to get the maximums, let's say, if I want to get the maximum, if the stream is of integers, 1, 2, 3, 1, 2, 3, 2, 1, 5, 1, 7, okay? So if I do, this would all be, let's imagine that this is all on one partition because the reduce is called on a partition level. So the resulting would be, for example, if I want to get if I'm doing the reducing by finding the maximum, then the outputs of this operator would be 1, 2, 3, 3, 3, 5, 5, 7. So this would give us at a given moment with this reduce function, we would get the current maximum in a given value. So for example, this is a nice use case for this task. So I want to get in a given moment all the time, I want to have the maximum value for my sensor type. I want to have the maximum humidity, the maximum pressure, the maximum temperature, and the maximum carbon monoxide that has been measured on for the given sensor type. So what will I do? I will call the kit stream over here and call the reduce method. The reduce method expects a reduce function, new reduce function, sensor data, and this function has one, this functional interface, sorry, has one method, one function, that's the reduce function, which accepts two arguments. This would be the current reduce value, and this would be the new value. And we need to define a way how to combine these two into one data, one sensor data that will be saved as the reduced value. Okay, so for example, um, over here, so when it comes to 1 and 2, that's 2. When it comes to 2 and 3, 3 will be sent out and 3 will be saved as the current reduced value. When it comes till what's next, 1 to 3, okay, when it comes 3 and 2, 3 is the maximum, so 3 will still be the reduced value. 3 and 1 still 3. 3 and 5, okay, now 5 is larger, then this should be the new value. And we want to have something of the same logic, so we want to do reducing by the maximum in this task. So we can maybe just do a simple comparison. So if sensor data dot get value is larger than t1 get value, and I will rename the variables over here. In that case, we will return the sensor data. Otherwise, we will return the t1. This can be easily made into a ternary operator, something like this. So this would be much simpler, and this can go into a lambda function. No exception is being thrown. I just want to rename this. This would be new. Oh, actually, can't do it new. New data. This would be old data. Just so that the variables have more of a symbolic value. Okay, let's make this into a lambda. And let's save this into a stream. So let's call this reduced stream or rolling max stream. Let's name it that way. This would be a single output stream operator, or that's a data stream in behind. And we will call the print to this rolling max stream. So let's take a look what happens now. Okay, so let's look, for example, we have temperature. Here is temperature. Let's look all the way for temperature. 24, 24. Then a new maximum comes. That's 28. Then 28, 28, then 29. And then that's the reduced value. 29 again. No new maximum. 29, no new maximum. No new maximum. Probably that would be it, or we'll find a bigger value. Let's see. 48, here it is. This is the anomaly that has been generated probably. Yep. And this won't get changed at all. Maybe when we get a new anomaly for the temperature, it would be probably all the time 48. So that's the goal of the reduce operator. Yep. Still 48. The next operator that we are going to see, and this is one of the most important operators that you can have in Apache Flink, is the window operator. So, and this window operator can be called again only just on a partitioned kit stream, not on a regular stream. What does this window operator does? This window takes all of those four partitions, let's say temperature, humidity, CO, and what did I miss? Temperature and pressure, and on all of those partition, it is again partitioning the data. It is sampling the data into time time windows. So before I explain how this works, let's go over the types of windows that exist. So Apache Flink supports four kinds of windows. The first kind of window are the tumbling window, or these are windows that have a fixed size and they do not overlap. So for example, let's say that the window size here is 100. So this is from 0 till 99. This is from 100 till 199. This is from 200 till 299, etc., etc. So these are the partition, user 1, 2, and 3. Let's say that our data stream has three partitions for these three users. And these are all of the windows that are going to be generated on all of those partitions. So we will have a total of 15 windows. Three partition, 5 windows per each. That's 15 windows over here. Another type of the windows is the sliding windows. They are, again, each of them is called to all of the partitions separately, completely independent one from another. But the sliding windows are also known as overlapping windows. So they have a fixed size, but they also have a slide parameter. Okay, the slide parameters means what is the slide from the current start till the next start of the window. So this is the slide, for example. So it started here on 100 and ends on 200, but the slide is 100 over here. So the size is 200, but the slide is 100. So this window starts from 100 now because that's the slide. Then the third window starts from 200, the fourth from 0, 1, 2, from 300, from 400, etc., etc. So these windows are overlapping between themselves. Next, we are going to have the session windows. So the session windows, they detect a gap. So they try to group the data on each partition over here. They try to group the data into windows that will have a given start and end. But the start and the ends, so the start of the next window, is defined in that way if there is a session gap from the end of the previous window that is larger than a user-defined session gap. Okay, so for example, if this is 100 and the session gap is 200, so if after 300 milliseconds timestamp there is no data, that means that we can start a new window over here, the window 2. That's how the session windows are made. And the fourth type of windows are the global windows. The global windows, they don't have a start and end, so they are not actually time windows. The previous three can be considered as time windows, but these are not time windows. The global windows are starting and never ending, except if you define a custom trigger, and this trigger will say, okay, this element satisfies this condition. Okay, then I will proclaim this to be end of the window, and a new window will now start on this partition. So that's how it goes. If you don't do it with the trigger, then it will never, never, never end. So how do we do the window link? Let's go back here. The window link, as we said, if we want to run the window operator, it has to be a kit stream. But we also have another option for window all as an operator. So this is window all over here. And the window all can be called only on a regular data stream. So this data stream shouldn't be partitioned, but there is a slight warning over here. This is in many cases a non-parallel transformation. All records will be gathered on one task slot for the window all operator. So this is just as a warning. So if you can provide partitioning in your application, that would be the best way to develop an Apache Flink application. So how do we create a window stream? From window, the returning type is window stream. From window all is all window stream. Let's just do that over here in this exercise, just to show you how can you declare the window type. So this is the rolling max. Okay, I will comment the rolling max and the reduce operator over here. So just to see how it works with windowing. So the kid stream is kid stream. We can just say window, and over here we expect a window assigner. And for all of these 4 types of windows, there are exact windows assigners that you can call. For example, for tumbling, you can call tumbling event time windows, and then they have a static method off. And here in the static method off, you have to do time. And you go here milliseconds. So on every 2 seconds or 2000 milliseconds, I want to generate windows. This is, as we said, a windowed stream. Here it is. For the windowed streams, for the time windows to work, this tumbling, we can do it sliding. The sliding expects two arguments, the size and the slide. So slide 1000, size 2000. Then you have the session window, event time session window, with a gap of, let's say, so whenever there is a 1000 milliseconds inactivity between the data, that is where you cut and you proclaim, okay, left from here is one window, right from here, it's the start of the new window. And what else we had? The global window, right? Yeah. Global window .get. Let me see. I don't think that's the right way, but let me verify here. Global windows. Global windows dot create windows and then create. Yeah. This is how we do it. Just this won't return this object. So over here, it would be a normal window because, as I said, still not working. Just a second. Let's rerun it over here. Yeah, it's global window. So the global window, as I said, is not a time window. It's a different kind of window. So here, if you want to create a global window, you have to call this add trigger or register trigger. Actually, it would be after the window operator, sorry, trigger here. And you will have to define a concrete trigger over here. So we are going to see all of these windows in the next video, and we will also see the operators window apply, window reduce, etc. So this is it for the current video.